Yesterday we were talking about sending digital bits across a wire, or basically making a digital communication system, and also discussed very briefly the kind of problems that will come up if you try to do that. So the system we'll consider will be typically of this sort. There will be some board, some printed circuit board, on which you will have a chip. We'll mainly focus on IC implementations of transmitters and receivers. And this is the typical scenario today. So, and this could be any kind of chip. It could be specifically a communications chip, or it could be any chip that has to send data across to some other chip. And we have another board on which also we have a chip, and between the two boards is the medium of transmission. Now the medium of transmission can be anything. It could be another large board. It could be the PCB itself, and there are particularly large PCBs into which you plug in a lot of smaller PCBs, and those are known as backplanes. It could be a cable. So, an example of a PCB is you will have the memory chip and the processor on the same board, and they have to communicate with each other. And as you know, the speeds are pretty high now, right? Approaching or even crossed 1 gigabit per second. And you could have a cable. So, examples of this are Ethernet or USB. And also you can have an optical fiber. So these are some examples of what can be the medium of transmission of data. So the medium connects to the board, perhaps through some connectors. There will be something here, and then there will be traces on this board, and the chip connects to the periphery of the board. Okay, so this is how it typically is. And on the chip itself has a large package in which you have a small piece of silicon, and that small piece of silicon is connected to the periphery of the chip. So data has to go from this piece of silicon here to this piece here. Okay, so it has to cross the connections on the package, on the board, and through the medium, and on this board and back into this chip, right? And we'll imagine a symmetrical situation, meaning we'll assume that the two sides are the same. That is, it's not like one side wants to send data and the other side only wants to receive it, right? The both sides will want to send and receive data. So that's the kind of situation that we'll imagine. So what are the type of problems that we may encounter? So yesterday we said that one of the things that we discussed was no wire is a perfect wire. It's not a perfect conductor. So it has resistances and parasitic capacitances. Because of that, what happens is the representation of a wire is with distributed resistors and capacitors. So what happens because of this? Firstly, if you apply a step on this side, here we have a capacitor. So the output voltage will not jump up immediately, right? So it cannot. So it will take a long time to go up. So there is a delay. That is one of the effects, and delay itself is not a big problem. The bigger problem is, for instance, if you send a pulse that is short enough, it could be that the output side, the pulse does not reach the intended value. Okay. For instance, yesterday we were considering a case where symbol 0 was represented by -1 volt and symbol 1 with +1 volt, and the thresholding value is 0 volts. That is, anything above 0 volts is considered a symbol 1, and anything below 0 volts is considered symbol 0. Okay. In this case, we intend to transmit symbol 1, but it remains symbol 0. Okay. So this can lead to errors. So the first problem is high frequency attenuation of the medium. So what I wrote here was attenuation. So high frequency attenuation, because clearly at very low frequencies, whatever voltage you apply here appears at the output, but at high frequencies it won't. So you have a varying attenuation as you change the frequency. That turns out to be the problem. Exactly how it creates problems we will see afterwards. Yeah. So this is one of the issues. What happens because of this is known as intersymbol interference. Again, all these things will be defined properly. What this means is, you send a pulse for a certain interval Ts. Let's say this is the bit interval. At the output, if there is no intersymbol interference, there will be an effect of this pulse only within this interval Ts. Okay. So in this case, for instance, there is negligible intersymbol interference. Whereas if you have a lot of high frequency attenuation, it turns out that it takes a long time to go up. It doesn't go up immediately. Also, it takes a long time to come down. So the effect of this pulse is apparent even well after the pulse. Okay, meaning this is supposed to be one symbol and this is supposed to be the next symbol and so on, but this symbol has an effect in the next symbol interval and perhaps the next one and the next one and so on. So each symbol has an effect over multiple symbol intervals. That is known as intersymbol interference. So we have to find a way to get rid of it. Now there is another issue here that also causes intersymbol interference. That is, this is not a uniform medium, right? We have connectors here. We have also some kind of connections here. Connections meaning they are impedance discontinuities. It's not a single transmission line that goes from one side to the other. So the impedance of this, firstly, it may not be well controlled. Even if it is, the impedance of this part may not be exactly same as this part, which may not be exactly same as this part. Now if you have a cascade of transmission lines of different impedances, you will get reflections. Okay. For instance, let's take a case where, so I have a voltage source with some resistance R0. Let's say it's connected to a transmission line whose characteristic impedance is R0, and this gets connected to a different line whose characteristic impedance is R1, and this is terminated in R1. So each transmission line is terminated perfectly on one side. Okay, but at this point you have an impedance discontinuity. So because of this you will have reflections, and it's also not the case that one side will be terminated perfectly. You can have incorrect impedances on this side also. So because of this, what happens is, if you apply a step, what you get at the output is not a simple step. Depending on the relative values of impedances, it can do something like this, or it can go up and come down, right? There is a variety of cases depending on the values of R0 and R1. And also, if these impedances are different, then it won't reach the steady state value immediately. It will oscillate for a while, oscillate for a long while before reaching the steady state value. So if you have any questions at any point regarding anything, stop me and ask me immediately. Okay. So you remember the basic transmission lines, right? You know what happens if a transmission line is terminated by something higher than the characteristic impedance, lower than the characteristic impedance. So the second problem is impedance discontinuity. Now that also causes intersymbol interference. Let's see how. So let's say we have, so I apply a step Vs. What do I see here? What will I see? Let's say R1 is greater than R0. Okay, what will be the value? So let's say this is a 1 volt step and this starts from 0 volts. The output is also at 0 volts initially. What is the final value of the output? What is the final value of the output? Yeah, it's just a voltage divider. This is a piece of wire. Once it reaches steady state, you can apply a DC analysis. So this part will be R1 by R1 plus R2 volts. R1 by R1 plus R0 volts. But what happens in the middle? Does it do this? Will it be a step of size R1 by R1 plus R0? What will it be? Firstly, when will the output start changing? Have you guys done a course on transmission lines? EM, how long ago? Line delay. Okay. So let's say the delay is some TD. So then the output changes after a delay TD. So what happens after that? It will go to R1 plus R0 by R1 minus R0 immediately, or will it take another step? No, there is no capacitance, but the transmission line is, yeah. So it will be something different from the steady state value. In this case, what happens is, so what will be the voltage at this point? If I measure the voltage here, what do I get? You will get half. Immediately it will jump to half the value. Okay. And what happens after that? What should be the steady state value here? It will be the same thing, right? It will be the same as the other case. So in this case, actually there is no reflection on this side because this side is terminated correctly. So it won't ring. I mean, it's not like it's going to oscillate forever. It's not going to oscillate indefinitely, right? So there will be only one reflection from this side, and when the wave travels back, it will be perfectly terminated. Okay. So if you look at this end, X and Y, so this is Y, this is X. At X, after 2 times TD, it will do this. What will it do at Y? At TD, it will do what? Why can't it jump at Y? I mean, I don't know, you tell me. No, incident voltage is half a volt. Okay. And the reflected voltage is, it will be just half a volt, or it will be this voltage. R0 by R1 plus R0. Or R1 by R1 plus R0. It should be, right? In this case, it will be. So there is no reflection on the there are no multiple reflections in this case. Yeah, that's right. That's it. I mean, nothing comes back. Nothing comes back after TD in this case. So, in this case, if one side is perfectly terminated, what you get will be a delay. So, what happens if this is now a different? This is R0 prime, yeah? Input impedance of the transmission line. The characteristic impedance is R0. That's what I'm saying. Yeah, but when will you see the input impedance of the transmission line? See, if you have, so are you talking about this voltage? Why is this half? Okay, R0, R0. The question is, this is terminated by R1. The input impedance is something different from R0. Does everyone agree with that? So the question is, why did I write half a volt here? Is half a volt correct or not? So at the starting of the transmission line, the point X, initially I said it steps up by half a volt. Is that correct? Yeah. When will you see the effect of this impedance? Only if the wave goes and comes back, right? So it takes a finite amount of time. So that is 2 TD. So only after that you see the effect of that impedance. So at the start you don't see the effect of R1 at all. So let's say you replace this also with R0 prime, which is different from R0. What happens in that case? Okay, so what will that mean? Okay, it won't go to half a volt. And what happens? So this voltage will be different, you are saying. So it will go to a different voltage. What happens after that? So you can work it out. It's a function of the reflection coefficients. You have a reflection coefficient on this side which is related to R0 and R1, and on this side which is related to R0 prime and R1, R0 prime and R0. Okay. So it turns out that if both of these impedances are greater than R0, what you will see will be something like this. I mean, it doesn't maintain the amplitude, it goes on decaying. Okay. And finally it reaches a steady state value. What is the steady state? I mean, it approximately reaches steady state value. What is the steady state? So it is R1 by R1 plus R0 prime. Okay. Not R0. So the DC solution to this is only related to this and this. Okay. The transmission line is just a wire. So it has to reach this asymptotically. So what it will do is something of this sort. And these, I drew it as though they are unequal. All these periods are equal. What is this equal to? 2 times TD. And if you have a large enough difference between R1 and R0 and R0 prime and R0, these can be very different from the steady state value. That is, the amplitude of ringing can be quite a bit. So what is the problem here? How? Actually, yeah, you need two conditions. If the amplitude is large, or whatever the amplitude is, it will result in symbol interference if this TD is large enough. Okay. If this TD is very small compared to your symbol period, then maybe your symbol period is this much. You note that this always happens, right? Whenever you just connect a wire between 2 points, this always happens. But usually the effect is masked because like for instance in the low speed experiments that you run in the lab, this TS is much more than the time of flight delay, etc. But if it becomes closer to the delay, then you will have problems. So for instance, if your TS was only this much, so you can see that there is significant effect well beyond TS. Okay. So this also creates intersymbol interference. And of course, the intersymbol interference becomes particularly annoying when the impedances are different from the characteristic impedance. That is, the transmission line is not terminated very well. In that case, you will have a large amplitude of reflection, so you will have a large amount of intersymbol interference. This also creates intersymbol interference. Now there are further problems. I said that it's a symmetrical situation. That is, both sides are transmitters and receivers, and they are transmitting data both ways. Now how do you transmit data both ways? So one way is, you have 1 and 2. Let's say we are talking about a pair of wires for transmitting data. You can have a pair of wires for transmitting data this way and another pair for transmitting data this way. Okay. So this is one possibility. Another possibility is, you transmit data both ways on the same pair of wire. So you can do it both ways, right? So which is better? First one. Why? Rate of transmission is more. Why is that? Yeah. So you can transmit data simultaneously. When you have it separately, definitely that's the intention. So this is known as, actually this is not duplex at all. So we can have bidirectional transmission. That is because we have separate channels for going this way and that way. Okay. What is the disadvantage of this? More wiring. Basically, you need more hardware in this case. That's the disadvantage. So for instance, I mean, you can have a PCB and you need now double the area on the PCB to transmit it both ways. And remember, you can have a large number of these things. I am not implying that there is only one transmitter and one receiver on each side. Okay. So there could be lots of them, and it needs more hardware. So that's the disadvantage. Now, when you have this, how do you transmit data bidirectionally? Handshaking should be there. I mean, what do you actually do with the handshake? So basically, you're saying they won't be transmitting simultaneously, right? So you're saying for some time you can transmit this way, and for some other time you can transmit the other way. Okay. So that is known as half duplex. And what's the disadvantage of that? We need an extra signal. And that's okay. Let's say that is not a big problem. No, see, in half duplex, the problem is if each channel supports, let's say, 1 gigabit per second. This is the maximum data you can transmit, maximum data rate you can transmit over this particular line. Now, with only one line, both sides together can transmit 1 gigabit per second. So you can only have half a gigabit per second for each side. Okay. So if you do half duplex, you are restricted to half the data rate. I mean, it doesn't have to be equal. I mean, maybe this side is 0.75 and this side is 0.25, but I'll just say half data rate. So you're reduced in speed because of doing this time division, right? No, in this one. In the second case, when this is transmitting, you will be transmitting at 1 gigabits per second, let's say for 1 second. And for another second, you can't transmit this way. So effectively, you can only transmit in the reverse direction, in the other. So let's say from t equal to 0 to 1 second, you go this way, and t equal to 1 second to 2 seconds, you go in the other direction. Okay. So if you look at the data rate from 1 to 2, it is half a gigabit per second. Right? And 2 to 1, it's also half a gigabit per second. Whereas in this case, both ways it is 1 gigabit per second. Okay. So can we transmit data simultaneously on something like this? Okay. Well, let's say we don't want to do modulation because this is broadband data, right? So yesterday we said that the data spectrum looks something like this. It's not a narrowband signal. And when, again, we'll go into details of all this, how a link limits the data rate, etc. But when I say 1 gigabit per second, that means that I can't really go beyond this, meaning I can't go to high frequencies well beyond this one. Now, if I have to have, let's say 1 gigabit per second data and separate them in frequency, I have to put it somewhere well above 1 gigahertz, right? This can be one way and this can be the other way. But if I do this, now this part is at a very high frequency, which I am assuming is not supported by this transmission line. Okay. It is attenuated severely. So I can't translate it to a higher frequency. So this is broadband data. You understand that, right? So if you have to translate it to a higher frequency, you have to translate it to very high frequencies. So can you just like throw caution to the wind and transmit both ways? Have you seen a system like that? Have you, I mean, do you know of any system in which data is transmitted both ways on the same pair of wire? Telephone, right? So there is only a single pair of wire on the telephone, but you talk and you can talk simultaneously also, right? Of course, you may not be able to hear the other person very well, but still you can talk. How do they do it? The regular telephone is not time division. No, the GSM stuff maybe, but then between, let's say you take regular phones, different levels of what? No, okay. How do you do that? What will be the voltage between these two lines? It will be the sum of what you send from this side and what you send from this side, right? What is the forward to work conversion? How? I mean, think about it. How do you measure voltage on a wire? You always measure voltages between two wires, right? I mean, do you see a common ground between your home and here and everywhere? So you want to send x of t in this direction on this wire, let's say. So let's say I have x and then I have the resistance and this is connected to the pair of wires and I have y here. X and y are different. Maybe x is my talking and y is your talking. Okay. What will be the voltage on this wire? What is it? X plus y by 2, right? And what do you want on this side? Y. You want y on this side, right? Y is being transmitted from here, so you want to receive y on this side. You already know what x is because you are generating x. So you can multiply this by 0.5 and subtract it. Here you get y by 2. And you can do the same thing on the other side. So this is known as echo cancellation. So the idea is you know what you are transmitting, so you can subtract it out. Of course, in reality you can't subtract it out perfectly, and there are limits to what you can do, but this works quite well. And telephone is not the only one in which you have this kind of full duplex. If you look at Ethernet, that is the gigabit Ethernet, there are 4 pairs of wires, and on each pair data is transmitted both ways simultaneously, okay, at a very high speed also. So each one is at 125 mega symbols per second, and each symbol has 5 levels. So you can do this, you can do full duplex transmission, but then you will have to cancel the echo. Yeah, it will be a lot more, it will be more complicated. So, for instance, I mean, in a telephone maybe you can get away with something like this. Basically the point is mentioning is that this is not x plus y by 2. This is x convolved with some impulse response, and this is y convolved with some other impulse response, okay. And depending on where you look on the line, whether you look at this side or this side, it will be different. But there are ways to get around that also. So if it is memoryless, this is what you would do, right? But if it has memory like this, meaning it is x filtered by some transfer function, y filtered by some other transfer function, what you need is you need some, this can't be just a multiplication by 0.5. This has to be a filter, and the filter may have to be automatically adapted. And that is what is done in a high speed system. So you can do full duplex on the same pair of wires, but the challenge is echo cancellation. And this is a big challenge because I mean the signal on this side is of the same magnitude as the signal on this side. Now when y comes here over a long transmission line, y has become small, but x is still the full size signal. So in fact your interfering signal can be much larger than the signal that you want to receive. But the saving grace is that you know what signal is interfering with what is the signal that is interfering with y. So you can try and subtract it out. But it's not an easy thing to do, right? Especially as you go to higher speeds, and as I said, these filtering functions are complicated. You will have to do more and more complicated circuitry to get rid of the echo, okay. So if you want full duplex over this, you have to do echo cancellation, and that is the challenging part. And if you have to do half duplex, that is fine. Then you don't have to do this echo cancellation, but the problem is you are sacrificing half the data rate. Or you have to try and transmit at 2 gigabits per second, right, for half the time to get the same total data rate. But if you do that, it's the same transmission line. So you will run into more intersymbol interference and more reflections and all those problems, okay. So one way or the other, you have to use more complicated equalization. This process of getting rid of intersymbol interference or some other additive effects is known as equalization. So you will have to use more complicated equalization in either case, okay. What about here? Is there a problem here? So here the problem is, of course it's not directly connected to the same pair of wires, but still these two will be close to each other. So what you transmit to this side will also appear at the receiver. So this is known as crosstalk. So this will also be a problem, and you will have to cancel it, and you may be able to cancel it if you know what it is that you are transmitting. Sometimes you can have neighboring lines or nearby lines which are from different chips or different communication channels, in which case you can't really predict it and cancel it off very easily. Okay. So this echo is the extreme case of crosstalk where you are applying signal to both ends of the wire. But in that case you are definitely you know what you are applying, so you can cancel it. In case of crosstalk, depending on whether you know the data or not, you may or may not be able to cancel it. For instance, again in Ethernet there are 4 pairs of wires, they are all twisted together. So what you transmit on wires 2, 3 and 4 will interfere with what is being received on 1. Okay. In fact, what is transmitted on 1, 2, 3, 4 will all interfere with every wire. Okay. So for each one you have to have cancellation schemes. But then you have all 4 channels being received on the same chip. So you know what is being transmitted, so you try to cancel it out. But again, it's not you can't just multiply it by number and cancel it. It has to be some complicated filter, and the filter has to be adaptive. So as you know, the Ethernet cable that you plug in can be from here to there or some 100 meters long. So the characteristics and the crosstalk and the echo that you get from 2 long cable and a short cable are very different. So not only do you have to correct for all this, but the correction has to be automatically corrected. the correcting function. Okay, the filter function has to be adaptive. So, in addition to this, you can have crosstalk and echo, and all of this is corrected by what is known as equalization. We will see what it is as we go through the course. So, in addition to this, as I mentioned yesterday, there is a further problem that you don't know where each symbol begins and ends. Okay, so you are just sending data, and the data is changing at certain intervals, but you don't know exactly when each one begins and ends and when to sample the data. Okay, so the other problem is the timing. Okay, this is to know basically to know the frequency and phase of the clock with which you sample the received data. So this you somehow have to get. So again, there are simple and complicated ways of doing this. One way is, of course, you send the clock also along with the data. So that is possible, but then that entails more channels. That is, you need one more pair of wires, which may or may not be desirable. So on a chip, typically you have a common clock going everywhere, so that is okay. So then the only problem is the frequency is well known in this case, right? You use the clock that you have a clock with which you generated the data, and you send the same clock to the other side. So the frequency is known. The problem is with the phase. The phase is not known, and you may have to correct for the phase. In the simplest of cases, the phase doesn't vary as much, and you don't have to do anything. In more complicated cases, you send the clock so you know the frequency, but you have to correct for the phase. And in even more complicated stuff, especially when it turns out that it is too expensive to have a separate link just for the clock, you will have to recover the clock, both the frequency and the phase, from the data itself. So that means you need to have some circuit for doing timing recovery. So these are the main problems in communicating digital data, right? So these things always exist. When you send data from one flip-flop to the next, it exists. But of course, you don't even think about it because you send the same clock. That works because the one flip-flop is synchronized to a particular clock, and you can use the data out and the same clock, and the next flip-flop also gets synchronized to the same clock. So this is a very special case of where the frequency and phase are known, and the distances are very short. As you go to longer and longer distances, you can still use the same scheme, but then the data and the clock can experience different delays. Now, if the delay difference becomes too much, if it becomes a good fraction of the interval of the symbol, then you can have a problem, because then you can be sampling the wrong bit. So this you know from some digital IC design. This is what is a clock skew, right? So you can end up sampling the wrong bit if your skews are too much. So there is no guaranteeing that the delay in the clock path and the delay in the data path will be the same. So you try to match it as much as possible, but at some point you can't do that. So then you have to try and recover the phase. Okay, you have to reconstruct the phase of the signal. At least the frequency is known. Then if you really think of communication links, then it's too expensive to send the clock across, right? The clock is also a high frequency signal. It takes too much power. You need an additional channel, so you normally don't do that. And there is absolutely no hope of having the right phase, right? Because you have all these kind of filtering functions. There is transmission line delay, and there is delay in the filters that you use for equalization and so on. So you can't really get the phase anyway. So what you do is you recover both the frequency and the phase from the data itself. So for that you need something known as timing recovery. Is to go through these problems, how exactly they are created and the magnitude of those things, and you will discuss techniques for equalization and timing recovery. Okay. So basically we'll look at just how you send and receive digital data. This is not over transmission lines which have high frequency attenuation or something. You just have a bunch of symbols, you want to send them and receive them. How do you do that? And this you already know. You have CMOS drivers and flip-flops and so on. That's what we'll use. We'll see the performance of those things. Then basically look at how transmitters and receivers are built. And then you may have to change the rate of the signal, meaning you have two signals at 1 gigabit per second. You may want to combine them and send it on a single link at 2 gigabits per second. The reason for doing this is again the size of the infrastructure, right? So you can always send data at low frequencies. Let's say I initially said sending data 1 gigabit per second is difficult, but that's okay. I'll have 100 pairs of wires and I'll send at 10 megabits per second. Then there will be no problem. That is true. It is true that at 10 megabits per second the transmission line may work perfectly, but the problem is now you need 100 pairs of wires. So that is the disadvantage. So you may want to actually increase the data rate deliberately to reduce the infrastructure, okay, reduce the number of channels. as the demand for data increases, the data rate also increases. And the way to increase data rate, I mean, you can't put 10 Ethernet cables together if you want 10 times the data rate. Right? The realistic solution is to make the cable a little better and also increase the data rate by a lot. We look at serialization and deserialization. Basically, you have a parallel set of data, you serialize it onto a higher rate, or you go the other way around. So then we can look at high frequency characteristics of transmission lines. In general, the kind of impairments that you get at high frequencies. Then we look at equalization techniques. So there are what are known as linear equalizers, which are basically the linear time invariant systems that you know of. Okay. Or at least linear systems, may not be time invariant. And there are nonlinear equalizers, mainly the decision feedback equalizer. Okay. Then we'll look at timing recovery schemes, and hopefully we'll have time to discuss some example systems.